Greetings everyone and welcome to the Flight Connections demo. In this demonstration, we're going to explore how two powerful graph traversal algorithms, breadth first search, BFS, and depth first search, DFS, work on a realistic airline route network. By visualizing cities as vertices and flight routes as directed edges, we can simulate how travelers move from one airport to another, and how computer algorithms find efficient routes or explore all possible paths through a network. We'll use Dallas as our starting airport, a major hub in the United States, and connect it to other airports through realistic one-way flight routes. The graph we've built includes cities such as Atlanta, Denver, Houston, Chicago, San Francisco, Miami, Phoenix, and more. Each route is directional, meaning flights may not necessarily go both ways. This setup gives us a mix of direct flights and multi-hop routes, perfectly illustrating how BFS and DFS behave differently when exploring the same network. Let's begin by reviewing what this program does. The program defines a directed graph using a map. Each airport is a key, and the corresponding value is a vector of airports that can be reached directly from it. In other words, it's outbound flights. For instance, Dallas connects to Atlanta, Denver, and Houston. From Denver, you can fly to Chicago or San Francisco, while from Houston, you can fly to Phoenix or back up to Denver. With this graph, we'll perform two types of traversals. Breadth first search, BFS, which explores all airports reachable within one hop first, then two hops, then three, and so on. Depth first search, DFS, which follows a single route as deeply as possible before backtracking and exploring alternate paths. Both algorithms will start from Dallas, but as we'll see, the paths they take and the order they visit airports are very different. Let's start with the breadth first search. In the real world, you can think of BFS as a traveler who explores all direct flight options first before taking any connecting flights. If you're standing at Dallas, BFS first visits every city that has a direct connection. Those are your one-hop destinations. Once it's visited those, it moves outward to discover all cities that can be reached with two flights, then three, and so on. This process naturally creates layers of discovery, where each layer represents one more hop or connection away from the starting airport. When we run BFS on our network starting from Dallas, we see the program print each hop level in sequence. 0 hops, because our starting city is Dallas. 1 hops to Atlanta, Denver, and Houston. 2 hops to New York, Miami, Chicago, San Francisco, and Phoenix. 3 hops to Boston, Charlotte, Los Angeles, and Seattle. Let's break down what this means. At 0 hops, we have our starting point, Dallas. At 1 hop, we have all airports reachable directly from Dallas without any layovers, Atlanta, Denver, and Houston. These are the immediate neighbors of Dallas in our graph. At 2 hops, we move outward 1 layer to cities reachable from those 3 airports. From Atlanta, we can reach New York and Miami. From Denver, we can reach Chicago and San Francisco. And from Houston, we can reach Phoenix and Denver, though Denver is already visited, so it won't appear again. This gives us a total of 5 new airports discovered on this level. Finally, at 3 hops, we see destinations that are further out, those that require 2 or more connecting flights. From Chicago, we can reach Boston. From Miami, we can reach Charlotte. From Phoenix, we can reach Los Angeles. And from San Francisco, we can reach Seattle. When you look at this output as a whole, BFS provides a clear snapshot of how far each airport is from Dallas, in terms of number of flights. This is exactly why BFS is used to find shortest paths in unweighted graphs. It always discovers the closest nodes first before exploring deeper connections. Now let's contrast that with the depth-first search, the DFS process. If BFS is like a traveler exploring all nearby destinations first, DFS is like a traveler who picks one flight route and follows it as far as possible before coming back to try another path. The DFS algorithm uses recursion to keep track of where it is in the graph. It goes deep along one path, exploring each city's outgoing flights until it reaches a city that has nowhere else to go, or until it hits a city that's already been visited. At that point, DFS backtracks, returning to the previous city to look for unexplored routes. In our program, DFS is designed to show this process clearly. Each time the algorithm visits an airport, it prints out which city it's exploring, which flight route it's following, and when it backtracks. The output also includes indentation to indicate the depth of recursion, giving us a visual representation of the algorithm's call stack. How far we've gone down one route. Here's what part of that output looks like. At the top level, we start from Dallas and take the first outbound flight, in this case, to Atlanta. From Atlanta, DFS explores the first available route, flying to New York. Since New York has no outgoing flights, DFS immediately backtracks. Then, back at Atlanta, DFS explores the next available route, this time to Miami. Miami leads to Charlotte, which also has no further destinations. So, DFS backtracks again, first to Miami, then to Atlanta, and finally to Dallas once all of Atlanta's routes have been explored. After finishing all paths from Atlanta, DFS returns to Dallas and moves to the next city in the adjacency list, Denver. From Denver, it travels to Chicago, then to Boston. Since Boston has no connections, DFS backtracks through Chicago, and then Denver before exploring the next destination, San Francisco. From there, DFS goes on to Seattle. It then backtracks again to Dallas. Finally, DFS explores Dallas's last remaining route to Houston. From Houston, the algorithm follows flights to Phoenix, then to Los Angeles. From Los Angeles to San Francisco. Since San Francisco has already been visited, that branch is skipped. DFS then backtracks step by step until all cities have been visited and the traversal is complete. This recursive pattern of going deep, returning, and then moving on is the essence of depth-first search. Now that we've seen both traversals, let's summarize their key differences and the insights they give us about our flight network. Breadth-first search, BFS, treats the graph as a series of expanding layers. It's like throwing a stone into a pond and watching ripples spread outward, each ripple representing one more hop from the origin. BFS is perfect when we need to find the shortest path or determine how far one city is from another in terms of flight connections. Depth-first search, DFS, on the other hand, explores depth before breadth. It's like taking a single route to see how far you can travel without turning back. DFS is great for discovering all possible routes, detecting cycles, and understanding the structure of a network. In the context of this flight network, BFS gives us how many connections away each city is from Dallas, while DFS shows us the complete journey along one route at a time, including every decision, every return, and every backtrack. When BFS lists airports by hop level, you can think of it as showing the minimum number of flights required to reach each destination from Dallas. When DFS walks through each route recursively, it's showing the call stack in motion, how computers use recursion to explore deeply nested paths and then unwind as they return. The combination of the two outputs paints a clear picture of how traversal works. BFS is finding how close each node is in hops. DFS is understanding the full path structure and how the graph is connected. Thanks for following along. Copy the code into your compiler and add some cities to experiment with different results. We will see you in the next video.